Hello, everyone, and welcome to Lecture 12 of Data 102. The topic of today's lecture is uncertainty quantification for GLMs. So let's start with the big question, which is, why are we doing this? Why are we interested in uncertainty quantification? So let me try to answer this question using a few examples. In the first example, let's suppose that you were a quantitative analyst working for a hedge fund, and you just fitted a model to predict the future stock price of some stock. Okay? So let's say GME, since GME is so popular nowadays. So suppose your model predicts that GME is going to increase, the stock price of GME is going to increase by 10% within the next 24 hours. And you report this result to your boss. So what's your boss going to say? So you think the boss is going to say, okay, let's invest $50 million in GME. So more likely, your boss is going to tell you or ask you, what is your confidence level in this prediction, right? How certain are you is it that the stock price is actually going to go up by 10%? Or is there like a range of possibilities? And so if there's a range of possibilities, what is the range? Is it 5 to 15%? Or is it like minus 50% to plus 60% or something like that? Okay. And the decision that you and your hedge fund ultimately ends up making is going to be heavily dependent on this level of uncertainty. Okay, so now for a less sexy example. So the next example is going to concern quality control in manufacturing. And so if you read the news nowadays, there are new strains of COVID that are more infectious. So perhaps you want to protect yourself better by buying some N95 mask that has better protection. Okay, so the background as to why there's a 95 and N95 is because these masks are guaranteed to filter out 95% of all airborne particles. All right, so it's really important that it's able to do this. Now here's a question: is it 95% plus minus 0.1%, or is it 95% plus minus 10%? In other words, what is the range of different filtration levels across the entire range of products, right? Because there's always going to be some, no two products are exactly the same. There's going to be some natural fluctuation because of because of different, somehow small differences that happen during manufacturing. Okay, and this is going to matter to you as a consumer, right? Because whenever you buy a mask, you don't want the possibility, no matter how small, that the mask you buy is only going to have an 85% level of filtration, for instance. Okay, and things become even more tricky when we talk about what happens when you have models that you want to use to guide decision making and life and death situations. All right, so suppose you have some heart condition and you need to go for some risky surgery like a heart bypass. Right, so you need to make the decision whether or not to have the surgery. Okay, so if you have the surgery and it goes well, then you have maybe a life expectancy of 20 years. And if you don't, maybe your life expectancy is only 5 years, right? But it comes to a catch, of course, because there's always a risk. And suppose the doctor tells you that, based on your profile, you have like a 2% risk of having some complications. Okay, then you would be very interested in knowing, so where does this 2% come from? How many people were studied to come up with this number? And furthermore, what factors is being taken into consideration here, right? How many people what about your profile has been taken into consideration to give you, by the model, to give you this 2%, right? So suppose you might have some genetic condition that makes it that I'm not sure that for your heart and makes it different from other people. And so you want to ask that has this model taken that into consideration as well, because that would also affect the risk level for you. Okay, so there are all these factors so first, okay, so what's the takeaway? So number one, being able to know how certain these estimates are is very important to decision making. And secondly, a lot of factors are relevant for trying to estimate for you to quantify uncertainty. Okay, so we're going to talk about a few of these in this lecture, but just bear in mind that this is a very big topic, and we're only going to be scratching the surface. Okay, so here's an overview of the lecture. Okay, so lecture is going to have two parts. In the first part, we're going to make some definitions. Okay, so we're going to introduce various types of uncertainty quantification, confidence intervals, and credible intervals. Okay, so these are two notions that are easily confused. So we're going to redefine them and tell you what the differences are. And then we're going to talk about prediction intervals. Okay. And then we're going to say what we want out of all of these intervals. Okay. So width and coverage. And we're going to say more about these two properties later. And then in the second half of the lecture, we're going to talk about some algorithms that you can use to do uncertainty quantification and to produce all of these intervals. Okay, so first we're going to talk about the Bayesian context that will allow you to get credible intervals. Okay, so this is pretty straightforward. In some sense, we already have done this. And then we're going to move over to the frequentist world and talk about how to obtain confidence intervals using models. Okay, but the main tool that we recommend you use is the bootstrap. Okay, so we're going to introduce the bootstrap again. You probably already have seen this in data 8 and data 100, but we're going to talk about this again. And then we're going to talk about how to apply the bootstrap to GLMs in order to quantify uncertainty for GLMs. And lastly, if we have time, we're going to talk about some other methods to get prediction intervals for GLMs in the frequentist setting. Okay, so what are confidence intervals? Well, so we start with some true distribution P data that has data as a parameter, right? And so the goal is to estimate this data parameter. And because we are living in the frequentist world, we generate data, or we imagine that we generate some data, x1 to xn, that are drawn RID from P data. Okay, so let's call this collection of independent samples Sn. And then we can use this to form an estimate for data. And we can either get a point estimate or we can get a confidence interval. Okay, so using Sn, we can construct some interval Cn. And this is going to be a function of Sn. All right. And it's going to give us some interval. So let me just draw an interval here. All right. And what we want is for this interval to contain data, the true parameter data, with some sort of guarantee. All right. So what guarantee can we get? Well, there's data that so the interval that we construct is based on the data that we observe, but the data that we observe is what happens in our data set. So we also want to know what happens in other hypothetical data sets that we could have observed in some parallel universes. Right? So to indicate that, let me demarcate Sn with a superscript of 0. So this is going to mean that these are the samples that exist in our world. And we imagine that there are also some alternate universes. Okay, this index them using the integers in which we draw other samples. And then we could have used these other samples to also construct confidence intervals. Right, so suppose this one looks like this. And now we have another universe. We get another interval. And then we can keep doing this. All right, and then we get a whole bunch of other intervals. All right, so we want these intervals to have a nice property. which is that if data is true parameter, right, we want data to lie within, say, 95% of all of these hypothetical intervals. Okay, we only see one of them, right? The only one that we see is Cn0, and the rest only exist in our imagination or in this thought experiment. But nonetheless, we want to say that out of all of these hypothetical intervals, the true parameter data is going to lie in at least 95% of these intervals. Okay, so writing down this in words, we say that Cn, the interval that we construct in our data set, or abusing notation, we can also say that Cn is the procedure that we use to construct this interval. Okay, so we are referring to both of these things. Okay, so we say that this has a 95% coverage if, with respect to 95% of hypothetical data sets generated from P data, it contains the true parameter data. All right, and it's very important to note over here what is random and what is fixed. So here, data is fixed. Okay, so there's no randomness in data. This is a fixed number. And on the other hand, the interval itself is random. Okay, so the 95% guarantee is with respect to the randomness and the construction of the interval. All right, and in the Bayesian world, we have credible intervals, right? And credible intervals are a completely different story. Okay, so here we have just one data set, and let me just call this data set X. X1 to Xn. And now this data set is fixed. There do not exist parallel universes where we could have other data sets. Right? And now we combine this data set with a prior to get our posterior P data condition X. And now we want to have a 95% credible interval for data, but this is now defined in a different way. So here's a definition. 95%, or to make it symmetric with the earlier definition, a credible interval with 95% coverage is an interval, let's call it Cn as well, and let's demarcate the boundaries for A and B, such that if I consider the probability of this interval with respect to the posterior, okay, so probability of Cn with respect to the posterior, and this is at least 0.95. All right, so if we have an interval that satisfies this, then it's a 95% credible interval. All right, so in some sense, this is easier and more intuitive than 95% confidence interval. All right, and the remark over here is that in comparison to confidence intervals, the interval Cn is fixed. Okay, so it's fixed based on the data that we have, and instead, data is what's random. All right, so we do not assume, recall that for Bayesianism, we do not assume some true model data. Instead, our posterior distribution is trying to reflect our belief. All right, so saying that Cn is 95% credible interval says that our belief is that this parameter data lies within this interval with 95% certainty, right, based on our belief. Right, and in some sense, this is something that is more natural to people when they think about uncertainty quantification. All right, and this is also possibly because in many settings, we are trying to reason about probabilities of events that are not actually frequentist in nature. All right, so if you're going to ask something along the lines of what's the probability that there's going to be an earthquake in the next 5 years, or what is the probability that you're going to get a promotion or you're going to get an A in this class or something, right? So these are things that are not frequentist in nature because you don't have an infinite series of repeating events that you can examine to get frequencies. So instead, these are just one-off. So if you want to reason about these things in terms of probabilities, they are in terms of your beliefs. Okay, so you can have credible intervals for such things, but not confidence intervals. Let's see. So I think that, and this also happens in politics as well, which is where, we also have a lot of probabilities involved. So saying something along the lines of, if you looked at the forecasting for the 2020 election, then if the poll is saying that President Biden had an 80% chance of winning, so this was based in nature. So that was, if it was like 80%, plus minus something, so that would be a credible interval and not a confidence interval. Okay, so we've introduced credible intervals and confidence intervals in general. Now let's talk about them in the context of supervised learning and GLMs, but all of this applies to supervised learning. So we're going to talk about this in that more general setting. Okay, so what do we want? Let's talk about the Bayesian setting first. Okay, so for Bayesian supervised learning, we immediately get some uncertainty quantification for labels. Okay, so what I mean is that after you fit your model, you observe a new sample and some new sample X new, and you want to know what the label of the point is, right? So maybe you're going to make some prediction, and we want to know what is our uncertainty in that prediction. Okay. And so the way we do this is that I'm going to use our posterior, and we're going to make use of the posterior predictive distribution. Okay, so let's write down some equations. So let's say we're given a new, let's say this. So using the training data, we have a posterior P of beta given X and Y, X train, Y train. And now we observe a new sample X new. Then it's very natural to make prediction using the MAP. So the prediction for y new is going to be equal to x new transpose beta MAP. All right. But then we also have the entire posterior predictive distribution, right? And we call that, so what is this? This is the distribution of y new conditioned on x train, y train, and a new feature vector x new. Okay, so we can use this posterior predictive distribution to quantify our uncertainty and y hat new. Okay, so we can use this to get some 95% credible interval for y new. And just to refresh your memory what this is, right? I.e., this is going to be an interval, I don't know, C new, such that P y new and C new with respect to the posterior predictive distribution. Okay, so let's shift this here. And let's write out what this is. Okay, so we want this to be bigger than 0.95. And since we know the distribution, right, we're able to construct such an interval. Okay, and this will quantify our uncertainty and our prediction given our Bayesian beliefs. Okay, and recall that over here, because of Bayesian, we don't really care about true labels in some sense, and we don't really care about a true model. We're just quantifying our belief based on our Bayesian model. Okay, so everything is based on this coherent set of beliefs based on a Bayesian model. All right, and in the frequentist world, what's the equivalent? Okay, so in frequentist supervised learning, and I should say that most of the supervised learning algorithms and perspectives that you've seen perhaps in other classes are in the frequentist setting, right? Because you assume that you have this infinite stream of samples and you observe some portion, which is the training data, and then you want the model to perform well on the remaining set of samples, right? So you might have a finite test set, but in theory, you assume that you have this infinite stream of future test samples drawn from the same distributions. So what we want is something similar, but it's no longer going to be a credible interval. Okay, so instead, we want to get, say, 95% confidence interval for y, for the label y, of some sample point x and over here we have so now over here that we're not making any assumptions about the model. So this is something that you might want to do. And so the hope is that you can get your model to help you. Okay, but there's no mention of what the model is over here. Okay, and it turns out that this is a lot harder than getting a 95% credible interval, right? Because 95% credible interval does not rely on reality to justify it. Whereas in this case, this is something that we need to be able to justify with respect to the data, the data model that is giving us our data. Okay, so this is a lot harder, and it's also a slightly different task. Okay, because note that there are two sources of randomness here. And trying to get a 95% confidence interval. So first one is when we're trying to estimate your regression function. All right, so we usually fit a model to try to estimate the regression function. And because of finite samples, there's going to be some uncertainty in this. But even if you are able to estimate this regression function exactly, there's still going to be some randomness left because there's going to be some randomness in the sample label. Right, so i.e., even after you condition on X, label Y is still random. And in some circles, you would see this being called aleatoric uncertainty. So that's a fancy name for this sort of uncertainty that you just cannot get around. And so this is harder than both credible intervals as well as confidence intervals. And so such intervals have a special name. Okay, so these are also called prediction intervals, right? Because they have to do with your predictions. And as I said before, these are a lot harder to achieve, especially for black box models compared to credible intervals. Let's now talk about the performance metrics for confidence intervals, prediction intervals, and credible intervals. All right, so there are possibly many different ways of trying to create these intervals, and we want to know whether an interval is good or not. So how do we think about things like that? Okay, so performance metrics for confidence, credible, and prediction intervals. All right, so what do we want? So the first thing we want is high coverage. And coverage is simply going to be for, in the case of the frequentist confidence and prediction intervals, it's going to be the frequency with respect to which in hypothetical data sets, the interval covers your true parameter or the true value of y, right? And typically we set coverage to be 0.95, but it doesn't have to be 0.95. It can be higher than 0.95, or it can be lower than 0.95. For instance, 90% is also a common convention for coverage, but this is something that you can pick. And then the second performance metric is going to be the width of your interval, right? And we want intervals that are more narrow. All right, so why? So this is because we do want to quantify uncertainty, but at the same time, we want a precise quantification of uncertainty, right? So any interval that you specify as your 95% confidence interval, for instance, if you enlarge it a bit further, it's still going to be a 95% confidence interval, but it's now less precise because you have included some range of values that you probably did not need to include. All right, so for instance, if you set the confidence interval to be the entire real line, okay, so that is a legitimate choice, but it's sort of meaningless, right? Because you're not saying anything about how your random variable behaves. Okay, so these are the two properties that you want, but the problem is that there's a trade-off between the two. All right, so there's a trade-off between high coverage and the width, meaning that the higher the coverage, the larger the width of the confidence interval, or this actually applies to all three types of intervals. So I'm just going to leave it blank here. All right. And so you're going to have to make a choice depending on what your requirements are. Okay, so high coverage and low width are your what you desire, and these are the performance metrics you can use to compare different intervals that you have to say which one is better than the other. Here's another notion that is also important. Okay, so this is the notion of validity, and in a way, this is something that we take for granted. Okay, so we say that a CI. Okay, so I wrote CI here, but this also applies to all three different types of intervals. So we say that a CI with coverage 1 minus alpha. Okay, is by convention we usually denote coverage using 1 minus alpha. So we say that this is valid if we are being honest about the coverage. In other words, if it has a coverage that is advertised. Okay, so in some sense, it's a meaningless definition. Okay, so when we talk about coverage, the assumption is that the confidence interval already has that coverage. But as we see in a moment, there are different types of validity, which is why sometimes we need to mention this word as well. Okay, so why are there different types of validity? Okay, so there are actually two types. Okay, so the first type is exact validity. And second type is asymptotic validity. And let me now mention the differences between these two. So exact validity means that the coverage, the advertised coverage holds in finite samples. Okay, so this means that no matter how many samples you have, x1 to xn, you can construct your confidence interval out of these samples, and it's going to have the exact validity that's advertised for that confidence interval, right? So if I say that this confidence interval has 95% coverage, and this confidence interval has exact validity, then expect this 95% coverage to hold with respect to all the hypothetical data sets that you can generate with n samples. On the other hand, asymptotic validity means that the advertised coverage holds, perhaps not in finite samples, but it holds asymptotically, meaning that we need the number of samples n to approach infinity. Right? So oftentimes when we construct asymptotically valid intervals, they're going to undercover, meaning that they have lower coverage than expected for small samples, and they only become valid in large samples. Okay, so these are the definitions. In the next optional video, I'm going to give you some examples of these two different types of validity. Here's an example of exact validity. Okay, so let's set up the following distributional model. Okay, so suppose we draw x1 to xn independently from some normal with mean mu and known variance sigma squared. All right, our goal is to estimate the mean then how do we construct 95% CI from mu? Okay, so we can use our sample mean and subtract 2 standard deviations divided by root n. Okay, and more precisely is 1.96. Okay, and we construct an interval this way. And the claim is that this is exactly valid. Okay, let's prove this. So I need to compute the probability of this interval, the probability that data lies inside this interval. All right, so I can rewrite this as follows. This is going to be the event that data minus the sample mean is less than 1.96 times sigma over 10. And now let me note that I know exactly what the distribution of the sample mean is. This is normal with mean mu. All right, and I should have written mu here. All right, so x bar is a normal random variable with mean mu and variance sigma squared divided by n, because it's sample mean. So I can rewrite things a little bit and do this. What do I need here? That's 1.96. And then I note that if I do this, this minus mu divided 1.9, divided by sigma. Okay, if you do the calculations, this is normal with mean 0 and standard variance. So I know based on my Gaussian CDF that this is going to be at least 0.95. All right, so I have exact validity because this does not depend on the sample size n. Okay, so this is an example that of a confidence interval that has exact validity. Now let's construct another example where we have a confidence interval with asymptotic validity but not exact validity. Okay, so example 2. Okay, so now let's consider x1 to xn to run IID from some uniform distribution with mean mu. Okay, and let's suppose that it goes from mu minus 1/2 to mu plus 1/2. Okay, so what's the goal? The goal is still to estimate mu, and let's see how I wrote this earlier. So how do we get a 95% confidence interval? Then I know that the variance of spa in this case is going to be equal to a quarter. Okay, so this is something you can compute divided by the number of samples n. So this means that x bar minus mu divided by 2 times then is going to converge to a standard normal. Hence, let's set Cn to be equal to the interval x bar minus 1.96 divided by 2 root n, x bar plus 1.96 divided by 2 root n. And to check that we have validity, I need the probability that mu lies inside Cn. Okay, so this is probability that x bar minus mu is less than 1.96 divided by 2 root n. Right, and I made a typo here. So I need to divide by square root of the variance, so that actually means I multiply by 2 times root n. Okay, so now I multiply both sides of this equation by 2 times root n. Less than 1.96. And now, what do we have? Okay, so if this were exactly Gaussian, oops. So if this were exactly Gaussian, then I can say that this is bigger than 0.95, but it is not exactly Gaussian, it's only asymptotically so. So what I have is that I need to take a limit, all right? So I need to say that limit as n goes infinity. Okay, so if I take limits, I need to write limits everywhere. Then only under this circumstance is do I have this bound, can I bound this from below by 0.95? All right, so hence, Cn is an asymptotically valid (95% CI). Okay, but it's not an exactly valid 95% confidence interval. In the next part of our lecture, we're going to introduce some algorithms that you can use to compute prediction intervals, confidence intervals, and credible intervals. Let's start with the Bayesian case first, because it's a lot more straightforward. And I'm going to go back to one of the notebooks that we used in the last lecture. Okay, so this was the one book, posterior predictive traits. Okay, so I already ran the first few cells. Okay, we are studying the wind turbines data set, and we fit a Gaussian model, a Poisson model, and a negative binomial model using PyMC3. Okay, and then there was this plot trace function from the RVS data, the RVS package that we can use. So let's run this, and we produce these plots here. All right, So we are interested in the first two plots on the left-hand side here. What we see here is simply the posterior distribution. Okay, so posterior, this is approximate because we're doing MCMC, and the two different curves gives us the results that we get from running MCMC twice. Okay, but they generally look the same, so we can take maybe the interpolation between these as an indication of what the posterior is. Okay, and now, in order to get a credible interval for either the yield and intercept, we simply have to look at this picture, right? We can just eyeball it that, say, between 0.18 and 0.186, 95% of the mass of the posterior distribution for the yield coefficient lies within these two endpoints. And so perhaps not just by eyeballing, 0.18 to 0.186 gives us 95% credible interval for this coefficient. Okay, so essentially the takeaway is that what we already know how to compute visually at least these credible intervals for the GLM coefficients. Okay, we can also afford to be a bit more numeric. Okay, so here, if you go, so this is the trace class, and now I'm going to look at some of the attributes. So I'm going to look at the posterior attribute, the yield attribute of this, and then values. And let's just look at posterior first. Okay, so this is going to give you our. Okay, so this is the trace is now I guess it's an inference data class. And if you go to posterior, you'll be able to see all of the posterior draws for each of these variables. And now you can look at the values by looking at the year attribute and then the values attributes. Okay, so now what can we do? So this is now an array. Let's see how big it is. Okay, so it's an array of 1,000. So 1,000 columns, so 1,000 draws. And now we can compute two rows because of two chains. And now, using all this data, I can try to compute my 95% credible interval. Okay, so what I do is this. I take this collection of values, so I'm going to call it coefficient posterior, and then I compute the 0.025 quantile and 0.975 quantile, and that's going to give me a 95% credible interval. Okay, so this is how to get credible intervals for the coefficients of a GLM. Now, I want to know how to get credible intervals for the Y predictions. Okay, so to do that, we need to do this pm.sample posterior predictive that we did for posterior predictive checks. And then recall that using this posterior predictive check data, you're able to do this plot. Okay. Yeah, so before showing the plot, let me just say that let's look at one of these, negative binomial. And oops, sorry, negative binomial PPC. So this is going to give us again the posterior draws, and what we're interested in now are the Y values. Okay, so these are the posterior Y values, and then these are going to give us. So then these are going to give us the posterior values for each Y sub I, and then we have this plot here. We plugged in all of the data into this plot HPD function from the obvious data set again, and then give us something to look like this. Okay, and previously we were using this to do posterior predictive check, but it's also giving us a credible interval for the Y values. And you can see that when the model is misspecified, as in the Poisson case, then the credible intervals may not actually match up with reality here. But this doesn't actually matter because for Bayesian predictive intervals, so Bayesian credible intervals, this is simply about expressing your belief. Okay, so it doesn't have to correspond to fitting the data, which is, or predicting well on the data, which is actually a frequentist notion. Okay, so this is more like an extreme point of view. And because as we said in the last lecture, you really want to do some algorithmic fit checks. Let's now move back to the frequentist world and talk about how to get model-based confidence intervals. All right, so in order to really have this make sense, we need to assume that the model that we're trying to fit is correct, right? Recall this means that there actually is a true parameter beta naught that is used to generate the model in this fashion. And then once we assume that this model is right, there's some heavy-duty statistical theory that allows us to control the estimation error. And based on this theory, we know that we have this normal approximation. And using this, we can try to produce confidence intervals. Okay, and if we run the stat-smallest package, this is exactly what it's doing. Okay, so again, I'm reproducing the slide from the last lecture. Okay, so after you run it, we have a point estimate for the coefficients, and then we have the standard error. Right, the standard error comes from this asymptotic theory that I showed you on the last slide, and because of normal approximation, we can use this to construct a 95% confidence interval for the coefficients. Okay, but there are some problems, which is that we have to assume that the model is right. And when the model is wrong, first of all, the coefficient may not actually make sense. And then secondly, even if the regression function is right, but somehow the noise that you assume is wrong, then the model-based confidence interval is going to give you the wrong result. Okay, so we want a way to get around that, and one of the solutions to this problem is to use the bootstrap. In this video, we're going to explain the mechanics of the bootstrap algorithm. All right, so I know that some of you have already seen this before in some previous classes like Data 8 or Data 100, but it's always good to revisit the material. And hopefully the way we're going to discuss bootstrap this time is a little bit different from what you've seen before, and this will give you some new insight as to what's happening. Okay, so the bootstrap is something that we use to get confidence intervals under the frequentist setting. All right, so we're going to work with the frequentist inference setup. All right, so we start with some true distribution, which we're going to denote P sub theta star. All right, okay, so suppose that this is some density. And then we're going to use this distribution to generate RAD samples, x1 to xn, and let's denote this collection of samples Sn. And now, from this sample, I can construct some estimator theta hat sub n, which is going to be a function of Sn. And theta hat sub n is going to be an estimate of theta star. All right, so the goal is to estimate theta star. Okay. All right, so now we already have a point estimate. The next question is, how close is theta hat sub n to theta star? All right. In other words, we want to do uncertainty quantification of our estimate. And the whole idea of the bootstrap comes down to imagining what could actually happen in an ideal world, right? So suppose we had an oracle that told us what p theta x star is. Okay, so this is kind of stupid because theta star is the parameter that we want to estimate. It itself is unknown. And if we really knew what theta star was, then there's no point in estimating it. But let's suppose that we do actually know it. And the point now is not so much to estimate theta star, but to quantify the uncertainty in theta hat sub n. All right, we can still construct this theta hat sub n even if we already know what theta star is. Okay, but if we know what p theta star is, then we also know the distribution of theta hat sub n because recall that data hat sub n is a function of Sn over here, right? And Sn is just going to be n IID copies of xi drawn from p data star. All right. And so if we knew p data star, we know everything about the distribution of data hat sub n. We know what the mean is. Mean is going to be data star. And we also know what the variance is. All right. And we know all kinds of other statistics like median, quantiles, etc. Okay, but let's talk about the variance, just to be a bit more precise. Okay, so in particular, we know the variance of data hat sub n under the distribution p data star of x. All right. And so we can use this and also other aspects of the distribution of data hat sub n to do uncertainty quantification. Okay, but we don't know this, of course, right? Because data star is a quantity that we actually want to estimate. So here's where the first big idea of the bootstrap comes in. Okay, so this is the first big idea. And this idea is to replace the distribution p data star and all of these computations with the distribution p hat sub n, which is going to be the case, and we're going to define this as a uniform distribution on the set x1 to xn, right? And this is also called the empirical distribution, okay, because it is defined in terms of the sample that we see. Okay, so at this point, after having seen our sample, the sample is fixed, and with that sample, we can define p hat sub n. Okay, and the idea is to replace p sub data star with p hat sub n. All right. So even though p data star may be a density, p hat sub n is a discrete distribution. Okay, so it seems as if they're kind of different. But if you think about this in terms of the CDF of both distributions, it turns out that under many settings, with a moderate number of samples, like n is equal to 50 or so, the two CDFs can be pretty close to each other. Okay, so this is something that you can try with many distributions using some simulations. And so this is something that is not unreasonable. In fact, we'll see that this actually allows the bootstrap to work pretty well. Okay, so now let's talk about what this means for the variance. So if p hat sub n is close to p data star, and we're not going to be too precise about what close means, then, so what happens? Then the variance of data n, data hat sub n, okay, this is the quantity that we really want, can be approximated by the variance of the same estimator, but now with a different distribution, which is going to be the empirical distribution. Okay. So this random variable here, so just to be clear, this over here now is going to be a function of x1 star xn star, where each xi star is going to be drawn ID from your empirical distribution p hat sub n. Okay, so recall now that the original x1 to xn are fixed, and now xi stars are drawn from that empirical distribution instead. Okay, so that's the first step, the first big idea of the bootstrap. And now we're going to go to the second big idea. And the idea is as follows. Okay, so we can actually compute this variance. Oopsie. Okay, I wanted to do highlights. So we can actually compute this exactly because we know what p hat sub n is. but it might be a little bit hard because if data head sub n is a complicated function, so we don't really know what it is at this point. We just we're just treating it abstractly. So it might be possibly be pretty complicated, in which case it might be hard to compute exactly what the variance is. Okay, so luckily there's a way around it. And the way around it is sort of suggested by what we did previously in the Bayesian unit, which is to do sampling. Okay, so we don't actually need to compute the exact distribution. We just need to be able to sample from it. And using by sampling, we are going to be able to get a pretty good approximation to this variance quantity. Okay, so that's the second idea. So we sample from P sub n in order to get an approximation of the functional or statistic. Okay, so this means that these are things like the mean and the variance, which are properties of the distribution. Okay, so in our case, we set an estimate of this variance, right, to be just, you know, the naive variance estimate. Okay, so that's what this be. So, and maybe let me use J to denote indices. So I'm going to have data sub n J hat minus data sub n bar squared. Okay, so this first quantity here, data hat with the J in the superscript is the estimate that we get from simulating xi star to x1 star to xn star one time, and now we do this b times, and so this is going to give us a plug-in estimate for the variance using simulation. Okay, so I'm going to write out the full algorithm in more details later, and now the idea is that if we simulate enough times, then the quantity that we want to estimate, in this case, it's the variance with respect to P sub n of data hat sub n. It's going to be close to this simulated estimate. And hence, okay, we can put the two approximations together. Okay, so let me copy this. Paste this here. Okay, erase this. Okay, so this is going to be okay, so we can put the two approximations together, and we see that the quantity that we want to estimate on the left-hand side is going to be given by the quantity on the right-hand side, and this is precisely going to be the bootstrap estimate. All right. And so this is motivating why the bootstrap is a good idea to pursue. Okay, so now I just want to make a few comments. First comment is that you don't have to use the variance. Okay, or rather, let's say there's also this idea applies to other functionals of distribution of data heads of n, like quantas, for instance, on the mean. And so by computing the quantas, we have a different way of trying to get, by estimating the quantas in this fashion, we can also use this to produce confidence intervals. And maybe there are also some other fancy uses of Bootstrap to do other things. Like, so Bootstrap is not just for doing uncertainty quantification, but can also be used for other things like debiasing, for instance. Okay, so it's an extremely flexible and powerful tool. And the next thing is that if you use the Bootstrap to get confidence intervals, then these intervals are only going to be asymptotically valid. Why? And that's because of these two approximations that we have here. Okay, so this means that these are not exact, and these are only going to hold in as n goes infinity. So the confidence intervals that we get out of them are naturally also only going to hold or be valid asymptotically. Okay, now let's write down the full Bootstrap algorithm. Okay, so what are we given? So the input is our sample x1 to xn, and our estimator data types of n. Okay, so what do we do? Okay, so we repeat b times the following. Okay, so the first step is to draw a data set for this Sn b. And I think it's convention to denote Bootstrap samples by stars. Okay, so this is going to be x1 star to, so this is the b sample, so I'm going to use b in the superscript as well, to x and b star. ID from px of n. And then we compute data head sub n b. And I think I should put a star there. Not quite sure what I did earlier. Yeah, so let's put a star here. To be equal to applying the estimator to okay, so for short, I'm just going to put SNB star. And now after we repeat this b times, we're going to get capital B capital B draws of data sub n star. And then we use the distribution of this entire collection. Data heads and capital B star to estimate some statistic that we want. Okay, so maybe we just want the variance of this collection or not. All right, so this is the meta algorithm, and we're going to see some examples in some future videos. In this video, we're going to take a step back from GLMs and talk about how to apply the bootstrap to one-dimensional distributions. Okay, so here, let's start by comparing the CDF of some distributions with the empirical CDF. So recall that this was the first step of the bootstrap approximation. All right, so here we want to say that the true CDF is pretty close to the empirical CDF so that we can replace the true distribution with this empirical distribution instead. Okay, so here the code is doing that for 3 different distributions: the Gaussian distribution, exponential, and half Cauchy. Okay, so half Cauchy is essentially half of the Cauchy distribution, which is this heavy tier distribution. All right, and for each one of these plots, the blue curve is the true CDF, and the red curve is the empirical CDF. And now if I run this code again and again, it's going to give me slightly different plots because in each case, I'm getting a different set of samples. But you can see that, okay, and I'm running this code with 20 samples, and you can see that with 20 samples, the CDF approximation is really pretty good. All right, there's some fluctuation, but it seems reasonable. And also, it sort of doesn't really matter how heavy tier the distribution is. Okay, so this approximation of the empirical CDF works pretty well, no matter whether it's the Gaussian distribution, exponential, or half Cauchy. Okay, so this gives us some confidence in the first step of the bootstrap process. Okay, so now let's talk about applying the entire process to estimate the distribution of the sample mean. And here we wrote some code for how to do the bootstrap. Okay, so it might be a bit insightful to look at what the logic of the code. Okay, so this function takes in a set of samples. All right, so the sample is already there. And then B, the parameter B is simply the number of repetitions that you want for the bootstrap. And this function is going to indicate what function of the samples you want to compute, or what function of the samples you're interested in. Okay, so in this case, we're interested in the sample mean, so we input the mean function. All right, and the whole idea of the bootstrap is to try to get some estimate for the distribution of the sample mean without knowing anything beforehand about the original distribution. Okay, and so for every repetition, I'm going to construct a bootstrap data set by drawing n samples from so I'm going to draw n samples and new bootstrap samples by drawing independently with replacement from the original set of samples. Okay, and this is done using the np.random.choice function. And after I draw this bootstrap data set, I'm going to apply my function to it, and that's going to give me a value data boot. Okay, and I do this capital B times, so 1,000 by default, and I'm going to return 1,000 of these values. Okay, and these 1,000 values is going to give me an approximation to the true distribution of data of the sample mean data heads. Okay, so let's run this. And here we're going to make a plot. Okay, so let's start with n is equal to 5. Okay, so let's start with 5 samples. And then here we get this plot. And so you can see that, well, there is some difference between the bootstrap distribution of the sample mean and the theoretical distribution of the sample mean. Okay, so there's some discrepancy, but it really seems to be pretty good. And this is kind of surprising because we are only using 5 samples. Okay, so every bootstrap sample is drawn RID from these 5 samples. Okay, and now if I run this cell multiple times, I'm going to get slightly different results. But all in all, it's not too bad, apart from, some cases that look like this. Okay, and using this bootstrap distribution, we can compute some statistics. For instance, we can compute the standard deviation of the bootstrap distribution. And we can see that, oftentimes it's pretty close to the actual standard deviation of the theoretical distribution of the sample mean. Okay, and then if we increase 5 to say 10, it's going to give us a better approximation. And now you see that the bootstrap distribution looks even more normal. Okay, and then I run this a bunch of times. It's pretty good. Okay, so even when the mean is pretty far apart, like maybe in this case, right, the general shape looks pretty consistent. Okay, so that's a good sign. All right, so now let's try to do a more rigorous investigation. So what I'm going to do now is try to compute the error and the mean. So difference between 0 over here. So the true mean for the sample mean should be 0. And the sample mean that we observe is simply going to be, so in a way, it's going to be the mean of the bootstrap draws. Okay, so it's going to be centered around here. And so the error in the sample mean is going to be this difference. So in this case, it's 0.04 or 0.03. And in order to get good uncertainty quantification, we want the estimated standard deviation and for the sample mean to be more precise as an estimate of the standard deviation than the sample mean as an estimate of the mean. Okay, so here we are running a simulation to do this. Okay, so I'm going to let n start from, okay, so let's see what n values are. Okay, so I'm doing this for n is equal to 10 to all the way to n is equal to 100. And I'm going to repeat stuff a bunch of times to make it, to remove some noise. And then for every n value, I'm going to first generate some n samples. And then I'm going to compute the sample mean. And I'm also going to compute the bootstrap replications of the sample mean. And on the bootstrap replications are going to give me an estimate of the standard deviation. And now I can compute the error between the estimated mean and true mean, and also the estimated standard deviation and the true standard deviation. And now I can plot it as follows. Okay, so you can see that the error in estimating the standard deviation is a lot less than the error in estimating the mean. And now if we switch this plot to plot on the log scale for the y-axis, okay, you can see that the rate at which the error in standard deviation decreases is actually higher than the rate at which the error in estimating the mean decreases. Okay, so the latter has a rate of 1 over root n, the former has a rate of 1 over n. Okay, so this is good. So this says that using the bootstrap, we are going to be able to get pretty good confidence intervals to quantify uncertainty in the sample mean. Okay, so why stick with sample mean? So we can try to do the same thing for the sample mean, sample median, and also the 90th percentile. Okay, so median 90th percentile are also other functions of your sample that you can compute. So we can try to understand the sample distributions using the bootstrap. Okay, but it becomes harder to say what the true distribution is. So we're going to use some simulations to try to plot the true distribution. Okay, so let's go ahead and run this. And okay, so it's going to give us a few plots. And now what we had before was this plot on the left-hand side, except that now we use more samples. I think we use 50, how many samples? Oh, I'm using 100 here. Okay, so I'm using 100 samples, and sample mean, the bootstrap distribution of the sample mean is already pretty close to the theoretical distribution. The bootstrap distribution for the sample median is not as good. Okay, so you can see that there's still some error. And then when we go to the 90th percentile, the bootstrap distribution of the sample 90th percentile is a lot, well, is even more different compared to the theoretical distribution. Okay, and this is not a fluke. We can just run this a few times, and we can see approximately the same results. Okay, so as we increase n, the approximations become better and better. But for the median, and even more so for the 90th percentile, you can see that the bootstrap approximation is way worse compared to that for the sample mean. Okay, and so now it's interesting to ask the question, why is this the case? Okay, and it has to do with this notion of smoothness of functions. Okay, so it turns out that the sample mean is all of these are actually smooth functions of your data, but the sample mean is a lot smoother than the sample median, which in turn is smoother than this 90th percentile. Okay, and the smoother your statistic is, the faster the bootstrap distribution for that statistic to converge to the theoretical distribution of that statistic. Let's now discuss one more function of our data, and this is going to be the sample maximum. Okay, so here I've written the same code as above, except that I changed the function to the maximum. So let's go ahead and plot the results, right? And as you can see, it looks kind of weird. So maybe we can try to improve this by increasing m. So let's first change m to, say, 200. And it still doesn't improve that much. Let's increase it to 2000. And still, you know, it looks kind of wacky. Okay, so the theoretical distribution is down here. The bootstrap distribution has this crazy peaks here. Okay, so what's happening? So if you think about what's happening for the maximum, right? If you're trying to compute the maximum of our data, then the theoretical distribution is going to, you know, as n increases, it's going to slowly shift more and more to the right-hand side because Gaussian distribution is unbounded. But for the bootstrap distribution, essentially we have a fixed set of 2000 samples, and we're trying to pick the maximum of them, depending on your bootstrap draws. Okay, so you're always going to be picking the maximum in this the bootstrap data set. And the bootstrap data set is always going to be a subset of the set of n samples, right? So the candidates for being the maximum are only, it's just going to be a handful, because these are going to be your outliers. Okay, so that's why you're going to have this spiky, weird-looking distribution for the bootstrap distribution. Okay, and no matter how much you increase n, it's never going to give you a good approximation to the theoretical distribution. And the mathematical reason behind why this is happening is because this maximum function is not a smooth function of your data. Okay, and as we saw earlier, the less smooth the function is, the worse the approximation of the bootstrap distribution to the true distribution. And in fact, when the function is not smooth at all, then the bootstrap completely breaks down. So it's not going to work at all. Okay, so after seeing all of this, let's go back to our slides and say what the main takeaways are. Okay, so what are the takeaways? Okay, so as n increases, the bootstrap does better. Okay, so with more samples, bootstrap does better and better. But there are other factors that affect how well it does. Okay, so it depends on the smoothness of the functional or function of the data. Okay, the smoother it is, the better the bootstrap approximation. And then also, apart from that, it depends on how well behaved your underlying data generating distribution is. Okay, so if you're generating from a Gaussian, then things tend to be better. If you're generating from heavy tail distributions, it tends to be worse. So we didn't see this at the level of the CDF, but it's going to, this applies at the level of generating the bootstrap distribution. Okay, and there are also some limitations. Okay, so as said before, the confidence intervals that we get through the bootstrap are only asymptotically valid because it requires this large sample approximation. And so in small samples that can break down. So that's why you have to be a bit careful with using the bootstrap. Okay, and lastly, it requires you to have a smooth functional. Okay, so if you try to do this for the maximum of a distribution, then the bootstrap is going to break down. Let's now talk about how to apply the bootstrap to GLMs. Okay, so ideally we would like to use some package to do this, but unfortunately Stats Models does not have good bootstrap support, so we have to write our own function. So here, this function updates what we had earlier in the notebook. So now it takes some data, x and y, and also some function of your data. Okay, so in our case, this function is always going to return us some coefficients of a model. And then we're going to create B bootstrap data sets to get B bootstrap estimates of this function value. Okay, so let's go ahead and run and put this function. And we're going to try to apply this to the winter ones data sets. So here I've written some functions to return the coefficients of the three models that we are familiar with at this point: the linear model, the Poisson model, and the negative binomial model. So we're gonna feed in these functions into our bootstrap higher order function. All right, so let's go ahead and get started on the linear model. Okay, so I run this bootstrap function, and it's going to give me this plot. Okay, so how do I read this plot? Every point here is going to be a bootstrap replicate of my coefficients, and I'm plotting, I guess, so each of these points corresponds to a coefficient vector. The x coordinate is going to be the constant coefficient, I believe, and the y coordinate is going to give me my coefficient for year. Right, and every time in my bootstrap, for every bootstrap data set, I get a bootstrap data set of x, a bootstrap data set of y. I fit my model and get my coefficient and I plot it. Okay, and these are going to give me all the points here. The x over here is going to give me my mean over all of these points, I believe. Okay, so that's approximately true. So this is the x over here is going to give me the coefficient from the fitted model without doing the bootstrap. Okay, so as you can see here, there's some spread. Okay, there's also this gap over here, okay, which seems kind of weird. But remember that we only have 17 data points for the Boolean turbines data set, so it's not entirely unexpected that there's some weird features going on. All right, so this gives us an estimate of the joint distribution of beta hats, the two coefficients of beta hats. And if you want, we can also use this to try to compute our standard error for both coefficients. Okay, so that's what I'm doing here. I compute the standard deviation of my bootstrap samples and says that bootstrap standard error for the constant coefficient is 1, and then that for the year is 0.07. Okay, so I can use this to get confidence intervals. And now let's see what is given to us by just running the stats models package, because recall that it also gives us some standard error. Now, the standard error here is from the model, so assuming the model is correct, whereas the bootstrap standard error does not assume that the model is correct. Okay, so you can see that it's a lot less overconfident compared to the model-based errors. Okay, so that's one reason why you prefer the bootstrap. We can do the same analysis for the negative binomial model as well as the Poisson model. Okay, so let's start with the Poisson. And again, we have the scatter plots that we can interpret in the same way. And similarly, we can also get standard deviations for the two coefficients. So recall back when we fitted the Poisson model using stats models package, we said that it was way overconfident. So we saw that both in the Bayesian setting as well as in the frequency setting. And here you can really see that the standard error for the year coefficient is 0.01. Okay, so this is definitely way too overconfident. And then when we do the bootstrap, it kind of corrects for this, right? So now our standard error is 0.016. So it's way better. Okay, so again, maybe it's still a bit overconfident, but not as bad as using the model-based error. Okay, so finally, we can do this for negative binomial, and it's going to be a similar story. All right, so let's just wait for the results to run. Okay, so using the bootstrap, for the year coefficient, I have standard error 0.035, and here using the model-based error, I have 0.043. Okay, so in this case, the difference between these two errors is not that big, which gives us some confidence that the negative binomial model is a better fit, or at least the fit is not too bad. Okay, so what are the takeaways from this? All right, so in all of these cases, we saw that usually the bootstrap standard error estimate is a lot less overconfident compared to the model-based one. And so this means that it's safer to use the bootstrap as opposed to the model-based errors, especially when you are when there's a possibility that the model you're fitting is wrong. And what do we mean by the model being wrong? Okay, so remember that there are quite a few assumptions for GLMs. Like the linear model had 4 different assumptions. And so we had an assumption about the shape of the regression function, and we also had an assumption about the distribution of the errors. All right, so by using the bootstrap, we can overcome misspecification about the noise assumption. So if the noise is sort of not what you want, then we can still, it still gives you good some error estimates for the true parameter. But if the regression function is wrong, then there's no such notion of the true parameter anymore. And in that case, what the bootstrap is giving you is not an estimate of the uncertainty about the true parameter, but instead it's going to give you, in a way, some kind of stability result, and it's simply going to be uncertainty in terms of the so-called best fit parameter, the parameter of the projected model. Okay, so let's go back to the slides. Okay, so what are the takeaways? Okay, so what's the advantage of the bootstrap? It can give you valid confidence intervals even when you drop certain assumptions. As I said earlier, the assumption about the noise distribution, and they're just less overconfident in general. Okay, so this is a good thing whether or not the model is right. Okay, so what are the limitations? So first, we cannot sacrifice all of the assumptions. Okay, so certain assumptions, the bootstrap does not, even if it fails, the bootstrap cannot overcome. And one of these is the independence noise assumption. Okay, so if the noise is not independent, then we can no longer use the bootstrap. And also it doesn't account for model bias, as I said earlier. So if the regression function is wrong, then bootstrap's confidence interval gives you uncertainty for not the true model, but the projected model. And another thing is that we can't really compute prediction intervals when the model is wrong. Okay, so when the model is correct, you can kind of do this, but when the model is wrong, there's no way that you can use the bootstrap to compute prediction intervals.